This is AP Precalculus Notes for Topic 2.6, Competing Function Model Validation. All right, bear with me as I read. Throughout this course, we will have many opportunities to work with and create models based on a given dataset. Three particularly important examples of this are linear, quadratic, and exponential models. Because these three types of models occur frequently in the real world, there is a heightened focus on them in the AP Precalculus curriculum. On the AP exam, students will be expected to determine which model is most appropriate given a set of data. There are a few strategies and methods that we can use to determine whether a linear, quadratic, or exponential model is most appropriate for the given data set. And here's a fancy table to give you some hints. I think that the most valuable thing for this assignment is to just pay attention to the general shape of the function. Again, if it can be modeled by a line, it's going to be linear. A quadratic can either be this concave up or it can be a concave down U shape. So a U shape. Or it can be something where we get closer and closer and closer to the x-axis and we shoot off really fast. That's going to be exponential. It gives you some examples of some other things that might be helpful, which we'll come back to if we need it. Just remember that repeated multiplication is exponential repeated multiplication. All right, so moving on to trying to figure out which of these graphs is either linear, quadratic, or exponential. We need to graph these points first, which takes a bit of time. I'm going to try to do this as fast as I can and as accurately as possible. I'm going to do 0, 11, 2, and 8.2, 4, and 5, or 6 and 2.3, 8 and -1, and we can see that that kind of looks like a line. Like if I were to just draw that line right there, it looks pretty good. Therefore, it's linear. Just judging on the shape. All right, graphing the next set of points. -1, 2, 1.5, 5.5, 4, 10.5, 6.5, 5.75, and 9 and 2.25. This, to me, it kind of looks like a general parabola type shape. So I'm going to say that this one is quadratic. Graphing the next one, we have 1, 10, 3, 5.2, 5, 2.4, 5, 2.4, 7, 1.3, 9.7. To me, I'm seeing this function that goes kind of like this. That's going to be exponential. And then finally, we have these set of points: -2, 2, 1, 3, 4, 4.5, 7, 6.75, and 10, which is off the graph, 10.25. Which is right about there. Again, to me, this looks like some sort of function that grows as an exponential, so exponential. All right, so important formula about residuals. Generally speaking, if you're trying to find the residual, it's the actual minus the predicted. That's it. All right. It can be used to do a few things. I'm going to talk about those in a sec. So let's read an example 2. Example 2, the weight of newborn babies can be modeled by a linear function for the first 4 months after birth. Selected values for the weight, W of t, in kilograms of a particular newborn baby are given in the table above, where t represents the number of months since birth. Use the regression capabilities on your calculator to find a linear model of the form y equals a plus bx for the weight in kilograms of this particular baby x months after birth. So we need to enter this data into a table, or into a table on our calculator. So I'm going to pull up my TI-84. Remember that if you have stuff on this, like for example, in my table here, I have stuff. So I'm going to get rid of all that. You're going to hit second plus to do a memory, and then 7, 1, 2 to wipe all the memory. So if I go to my stat edit now, you'll see everything is gone. I can enter the data correctly. All right, and next is going to be 3.2, 4.2, 5.1, 5.8, 6.4. All right, so when we have the data entered, we're going to hit stat again, go to the right and calculate. And notice that option 4 and 8 are linear. Option 8 looks similar to what we're asked to do over here of this a plus bx. I'm going to hit 8. I'm going to store my regression equation in alpha trace y1, and there is our equation. I'm going to go ahead and write that out again. It's going to be y is equal to a, which is 3.34, plus bx, so plus 0.8x. So there's our equation, and we're going to use that in part B to find what the baby weighs after 2.5 months. So this is going to be 3.34 plus 0.8 times 2.5. You can actually type this in manually, or the quicker way, since we've stored this in the equation y1, I can pull back y1 by doing alpha trace y1 in parentheses 2.5, and I can go a little bit faster and say this is going to be 5.34, just as a way to prove that you could have done it the other way. You could have done 3.34 plus 0.8 times 2.5, and you get the same, 3.34, I apologize. So 3.34, and you get 5.34 no matter what. In part C it says, hey, just kidding, you predicted 5.34, but it was actually 5.5. What's the residual? So as a reminder, residual from that last page was the actual. I'm going to spell actual minus predicted. The actual weight of this baby was 5.5. The predicted weight was 5.34 from above. And if I subtract those, this is going to be 0.16. So that's our residual. The residual is 0.16. And it has another question. I'm just reading here. Did our model underestimate or overestimate? Well, our model was 5.34, which is underneath the actual 5.5, so we were an underestimate. This next part is pretty key, and it's very important. So we're actually going to plot residuals on a graph, and there's two key components here. It is appropriate, so the keyword, it is appropriate if there is no pattern, without a pattern. No pattern means you did a good job and it's the right type of graph. And no pattern means I can't predict where the next point will go on the graph. So let's try that. I don't know if we'll need a calculator. We can come back to that if we need it. So let's go ahead, and this is the first time that we've seen in this class a residual plot. So it looked like they were trying to make an exponential equation, and they said, okay, here are all the remainder, all the bad things, the residuals, right? If I subtract the real values minus the predicted values, these are all of the values. So I can't tell where the next point is going to be. Is it going to be down there? Is it going to be up here? Notice that sometimes there's 2 down here, 2 down up here. Sometimes it goes 1 back and forth. I don't know where the next point is going to be, which means there is no pattern for that residual plot. And as I just stated over here, if there is no pattern, that's a good thing, and the data is appropriate. So this data has no pattern. So we can say that it is no pattern. So it's not B, it's not D. And because there's no pattern, it is appropriate. So the answer here is C. All right. Example 4, I'm going to read this. A group of AP Precalculus students used a set of data to create linear, quadratic, and exponential regression models. You can notice that this linear, quadratic, and exponential regression models. After creating the 3 models, the students created a residual plot for each model, see above. Based on the 3 residual plots above, which model was most appropriate for the data? And we have to give a reason. So I'm noticing that there is a pattern here. I can clearly see that if I move to the left, my point should be like somewhere over here, or some point over here if I'm going to the right. I know where this point is going to be because there is a pattern. Therefore, this is not an appropriate model. So it's not linear. Over here, I can see that the point is probably going to come down here and probably turn around, probably up here and probably going to turn around. I can see that there's some sort of like wavy type function here. This one has a pattern. I was able to predict what was going to happen. Therefore, this is not an appropriate model. I can predict what was going to happen. Over here for the exponential regression, I don't know. I know that it's somewhere in that region. It could be up there. It could be down there. It could be down there. I don't know where it's going to be. Therefore, that one has no pattern, which means that's the good one. That's the one that we actually want. The exponential regression model is the one that we want. So we'll say, based on the 3 above, exponential was most appropriate. It asks the question, give a reason. And you'll say, because the graph of the residuals has no pattern. Excellent. Moving on to example number 5. Bryan Passwater returns again in a new problem. Mr. Passwater hopes to make it into the Guinness Book of World Records by painting the world's biggest mural on the sides of several downtown buildings. His mural will consist of many painted circles of various sizes, where each circle is painted a different color. He wants to create a model to determine how much paint is needed in quarts for a circle of radius r. So, should Mr. Passwater use linear, quadratic, or exponential model to model the situation? Explain. So this one's kind of hard. There's not a lot of information aside from the fact that we are painting circles. So I know that if you're painting circles, you care about the area of the circles, and I happen to know that the area of a circle is equal to pi r squared. This is kind of the equation. I'm noticing here that this is a power of 2, therefore this is going to be a quadratic equation, and therefore it's going to be a quadratic model. So we'll say quadratic model. Does it ask us why? Yeah, explain your reasoning. Because area equation has a variable, I cannot spell, a variable to the power of 2. Power of 2 means it's quadratic. Okay, and part B. After creating his model, Mr. Passwater uses it to purchase different special paint colors to use on his mural. In this situation, do you think it is more appropriate for the model to underestimate or overestimate? Well, we don't want to run out of paint. So if our model is an overestimate, we'll buy too much paint, which is better than the reverse of that. If our model predicts too little paint and we buy that amount of paint, we might run out. So we want our model to be an overestimate. So want model to be an overestimate. So we buy too much paint as opposed to too little paint. We don't want to run out of paint. Excellent. And that's it for the notes. All right, so that concludes notes for topic 2.6 for competing function model validation for AP Precalculus. Thank you for watching.